Good evening, everyone, or at least good evening from where I'm speaking from. It's 11 o'clock here in the UK. I hope that you're doing well wherever you're coming in from. Now, this fifth session, I'm going to talk or start talking about the golden ratio and the way in which that shows itself cosmologically, but also how it shows itself within the design of the cathedral that I've been looking at for the last however many years, and which I've written about in the Cosmos in Stone. Now, cosmologically, Mercury is just in the process of going into retrograde, where it has that appearance of moving backwards, which is understood to affect communications. So that's something you can perhaps look out for. Let's get moving with the slides. Now, I'm beginning with this doorway here. This is the doorway to the sacristy in the cathedral in the city of Wells. Now, it's a significant doorway, being as it's the doorway into the sacristy. You'll see that it's off-center within its particular area, within the wall, if you see between those two sort of narrow pillars on either side of it. Now, the reason for that is because, or at least the apparent reason, is because it's at the golden section of the wall. Now, the golden section, I'll describe this over the next period of time. The golden section, of course, means cut. So the golden cut, it's a particular division of a line. And it's also sometimes known as the golden mean or the golden ratio. And this golden cut of the line is what actually defines the position of this doorway. Now, I'll describe that in a bit more detail, just as I go along. Now, the golden section can be understood as relating to a line. So if we're going to cut this line at the golden section, we're going to cut it at a particular position where it creates a significant mathematical relationship. So there it is, that line that has just gone in. And as you can see, it's cut the line into a shorter part and a longer part. Now, I'm going to refer to that shorter part and longer part as the lesser and the greater. Now, what's said about the golden section is that if the lesser is to the greater, as the greater is to the whole, then it's the golden ratio or the golden section. Now, I'm going to describe this in completely visual terms without using any numbers at all, because that can be quite useful, particularly for those who find numbers a bit of a challenge. Now, what that line that I just spoke is saying is that if the lesser is to the greater, so if the shorter part is to the longer part in the sense of their relationship, mathematically speaking, if the lesser is to the greater, as the greater is to the whole, then it's the golden ratio. Now, a key thing to understand about this is that both of these sections of line, the shorter one and the longer one, they both play the role of being a shorter part. Even though I don't describe this one as being a lesser part in that line, they are essentially both playing the role of being a lesser part. So this one is a lesser part in relation to this one, which is a greater part. But then this becomes the lesser part in relation to the whole line. Right, so bearing in mind that we have these two sections of line, which both in their own way play the role of being a lesser part. Let's now imagine that if we were to move this section, this cut of the line, if we moved it, say, for instance, slightly to the left, what that would result in is this lesser part would get a bit bigger in relation to its greater part, whereas this, as a lesser part, would get a bit smaller in relation to its greater part, which is the whole line. Now, of course, the equivalent opposite thing would happen if you put the cut ever so slightly to the right. So this would end up getting smaller in relation to its greater part, and so on. So that's a visual way of describing how there is this very particular thing about this cut of the line, in the sense of it creating a particular relationship between the parts and the whole. Now, the very interesting thing about it, bearing in mind that it's a mean, is that it's off-center. Because obviously when we think of a mean, we usually think of a middle place between extremes. But this particular mean is off-center, and it's a very significant one, as we'll see over the next few sessions, because I'm going to concentrate on the golden ratio for the next few sessions. There's quite a lot to point out in relation to it. Now let's go back to that image of the sacristy doorway in Wells Cathedral. So what you need to imagine is that these two pillars here, if we drew this line, say from here through to here, these two extremes of the line will be in the middle of those two pillars. And then if you, say, dropped a piece of string from the top of this pointed arch here, straight down, it would go down the middle axis of the doorway. Obviously, if you're standing in front of the doorway, you'd see it going through the middle. And it would be at this position in relation to these two extremes. Now, there's no practical reason why the doorway, or no purely practical reason why the doorway is at the golden section. If it was in the middle of that bay area, that's what the area is called, between the pillars. If it was in the middle, it would still go into the sacristy that it leads into. So it is, I think, quite clear that it's intentionally been put at the golden section. And I'll talk a bit more about this kind of symbolism, I think, in a future session, but in the sense of it being a doorway through from one, I suppose, one world to another, or from one level to another. This is how it seems to show itself in the philosophy of Plato. And I think I'll talk about the line divided into unequal parts. The analogy of the divided line is what it's called. I'll talk about that in a future session. Right, if we do look numerically at this line, let's say that that shorter part on the right has a length of 1, then the longer part will be the number that's associated with the golden ratio, which is 1.618. Now, it's one of these irrationals. It goes on to an indefinite number of decimal places without going into any repeating decimal pattern. So I've just put it to 6 decimal places there. So if the shorter is 1, the longer is 1.618. Now let's look at it in another way. Let's now look at that longer section of line, which, as I mentioned before, also plays the part of being a lesser part. Let's say that that is equal to 1. Then that would mean that the whole line would be 1.618. So what that would mean is that this shorter area here, if we're going to say that this is 1, this is obviously going to be 0.618, because then these two together would create the 1.618. Now look at these numbers that we've got here. We've got two 1s, and we've got these two incommensurable irrational numbers which differ to each other by 1. So 1.618 take away 0.618 is 1. And this is another feature of the golden ratio, that it always brings you back to the 1. Right, the next theme that I'm going to concentrate on, I'm going to sort of jump around a bit in these talks. I have to go through various themes to then show the cosmology nearer to the end of the slideshow. So what we're going to do is look at Fibonacci numbers. Now, as you may be aware, the Fibonacci numbers, they're really part of the whole golden ratio system, but similar to what I've been talking about in the past few weeks, these give rational approximations of the golden ratio, which itself isn't irrational. So the Fibonacci numbers, they create a sequence, and as we'll see, each pair of consecutive numbers increasingly approximate the lesser and the greater of the golden ratio. Now let me actually put something to that. Now look to the left of the screen, you can see the number 1 here. This is what we begin with the Fibonacci sequence. We begin with the first number, which is 1. Now the principle of this sequence is that we need to look to the number that comes before and add it to the number that we're on, and then that gives us the next number. Now, what can we do here? We have nothing before 1. So what we're going to have to do is repeat the 1 again. So this is a second number 1, but the difference between this number 1 and the first number 1 is that this second number 1 has something to relate to other than itself. So 1 plus 1 is obviously going to give us 2, which is the next number in the sequence. 2 plus 1 is 3. 3 plus 2 is 5, and so on. 8 plus 5 is 13, and we'll just carry on like this. This is how the sequence shows itself. Now we'll put 34 down there in the bottom left-hand side, and then we can go all the way along. So this is the first, I think, 15 Fibonacci numbers. Now, the next thing that we're going to do is look at each pair of consecutive numbers. And as we go along, looking at the relationship between these numbers, and obviously every pair of consecutive numbers that you can see here, except for what happens at the very beginning, as we move through the sequence, we end up with numbers next to each other, obviously a greater number next to a lesser number. And that relationship, increasingly, as you go through the sequence, gets closer and closer to 1.618 to 1. But it can never actually express the golden ratio, because the golden ratio is irrational. So it can't be expressed as a relationship of two rational numbers. But it's so close, really quite early on within this sequence, that we can use this in building. We can use this. And in fact, the doorway of the sacristy that I just showed you, properly speaking, it is actually at a very high number rational sort of division of the line, rather than being exactly at the golden section. It's a high number, not Fibonacci number. It's not in any of the sequences, but it is a rational relationship of two high numbers that gives you a very good approximation of the golden ratio. Right, what we do next, if you look at the two ones at the beginning, what I'm now going to do is divide each number by the one that comes before it. So 1 divided by 1 is obviously 1, 2 divided by 1 is 2. Now, from now on, every single relationship that I show you is going to be between 1 and 2, but more to the point, it's going to gradually get closer and closer to 1.618, and it'll eventually go to quite a few decimal places. So the next one, 3 divided by 2 is 1.5, then 5 divided by 3 is 1.666. Now, that's to one decimal place. So already we have 1.6, you could say, so we got it to one decimal place. Now, the next one, 8 over 5, is actually 1.6, and that's that. No more numbers. 13 over 8 is 1.625. Now, as you can see, 1.6, the previous one, that was a bit too low to be 1.618, whereas 1.625 is a bit too high. Now, this is what continues to happen through the sequence. Every single one of these calculations that we do, one will be too low, and then the next one will be too high, and so on and so on and so on. So it's a little bit like a pendulum swinging over the section itself, but the pendulum is gradually slowing down, you could say. It's gradually moving closer and closer to that ideal mean. So it's moving from time towards the timeless, you could say. But it never gets there because these are rational numbers, but it gets exceedingly close. Now, if we go 21 over 13, now we have 2 decimal places. And now we have very close to 3 decimal places. Now, if you look down on the bottom left, now we have it to 3 decimal places once we get to 89 over 55. And it just moves closer and closer each time. So now we have it to 4 decimal places, 1.6180. And then finally, just where we're going to stop here, we have it to 5 decimal places, 1.61803, and then it goes off. But already quite near the start of the sequence, we get an exceedingly close approximation of the golden ratio. Now, I'm going to focus on these numbers that I've highlighted in red, 5, 8, and 13, and I'll be talking about them a lot in the next session, because they're the numbers that are associated with the relationship, the orbital relationship between planet Earth and planet Venus. Now, more about that in the next session. I will refer to them again a little bit later on, but let's just look at these in relation to the division of a line. So it helps to explain the golden section a bit more. So back to our line divided at the golden section. It's also known as the extreme and mean division of the line. That's what Euclid called it. Right, there's 2 more lines, identical. Now, what I'm going to do with the first of these 2 new lines that I've put in is divide it up into 8. So we've got 8 equal parts, and the other line I'm going to divide up into 13. Now let's look at the top line. I'll highlight the golden section in red. Now, if we look at the line below that's divided into 8, you can see that very close. It's not quite the same as the golden section, but if you look at that division between 5 and 6, the one here highlighted in red, that's very close to being at the golden section of the line, but it's slightly off because it's a rational approximation, so it can't be precise. Now let's go down to the line of 13, and you'll see that where we divide by 8, we've got this very close approximation, but if we actually put in the line that goes through the section, you can see that 8 over 5 is just a little bit too much, whereas the 13 over 8 is just a little bit too little. Now, as I say, these sections of the line, which are rational, they'll gradually get closer and closer. Already, they're very close, as you can see. Right, now hopping to another theme, bear with me on this. What I'm going to talk about here is actually very similar to the Fibonacci numbers. I should add as well, actually, we call them Fibonacci numbers, what I was looking at before. Fibonacci, Leonardo of Pisa, he was an Italian, he was around in the 12th century. But just to say that the Fibonacci numbers were written about a long time before that. There was an Indian mathematician called Pingala who wrote about them, I think about 300 BC. That's a long time ago. So it's not that Fibonacci is the person who first brought them to light. He probably just heard them. His father was a trader in the Middle East, so he probably heard them, and then he wrote a book in which he mentioned something that alluded to the numbers. So that's why they've come to be called Fibonacci numbers, but they've been known about for a long, long time. And the design in Wales Cathedral that uses Fibonacci numbers was built before Fibonacci wrote his book. Right, so back to Lucas numbers. Now, Lucas numbers are essentially, well, much the same thing as Fibonacci numbers, but they begin from a different starting point. So what happens is you get a different sequence of numbers, but you follow the same principle. So if you look to the left, you've got the number 2 there. So that's how it begins. Rather than beginning with 1, it begins with 2. Now, I'm going to go straight to 1 from here. And then it follows the same sort of process as with the Fibonacci numbers. So from 1, we then 1 plus 2 is 3. 3 plus 1 is 4. 4 plus 3 is 7. 7 plus 4 is 11. 11 plus 7 is 18, and so on. So we just keep on going in the same way. But as you can see, the numbers that are coming up are different because we had a different starting point. Now, you do find Lucas numbers in the natural world as well as Fibonacci numbers. There's a good expert on the golden ratio, someone called Scott Olson. He's an American, and he's written quite a lot about the golden ratio. His wooden book about the golden ratio talks about Lucas numbers as well. That's right, so let's look at the calculations that we get. Now, as you can see, if we go to the beginning, 1 divided by 2 is 0.5, 3 divided by 1 is 3. And then as we go along, again, the numbers gradually start to get closer and closer to 1.618. Now, by the time we get to the end of these ones, you can see we've got it in 29 over 18 is 1.6111. And then it goes off again a bit up to 1.62, which is still obviously very close. And then if you look at the numbers below, again, it starts to go in very, very close until with this one here, 521 over 322 gives us 1.6180, so to 4 decimal places. So again, it just carries on. Now, it is actually a fact that you can take any 2 numbers, it doesn't matter, any 2 numbers that you like, obviously one being bigger than the other, and if you go through this principle of counting and then dividing, you'll always end up moving towards 1.618. So it is the very principle of growth. And so perhaps no wonder we find the golden ratio in the world of growth in this world. It shows, that's where it really shows itself a lot, the golden ratio in Fibonacci and Lucas numbers. Right, so that's Lucas numbers, essentially the same sort of thing as Fibonacci numbers, but just from a different starting point. Right, now, let me just go back. I You see how I highlighted these numbers? I forgot to mention 7, 11, 18, 29. So these are Lucas numbers, but they also show themselves in what I've been talking about for the last few weeks, which is the circle divided up into 22 with its diameter of 7. So the circle of pi, the approximation of pi, 22 over 7. So as I've mentioned in previous weeks, if the circumference is divided up into 22 equal parts, then you'll pretty much have 7 of those parts in the diameter. It's a rational approximation. It's not precise, but it's very close. Now, what I want to point out here are those 4 numbers that I just highlighted in the Lucas numbers, because these 4 numbers also feature in this pi diagram that you're looking at here. So 7, that's very clear. That's in the diameter. 11, you could say, is a semicircle. Now, 18 obviously comes from adding 7 and 11 together. So if you take a semicircle, if you take the diameter and a semicircle, then obviously you have 18. But then to add the extra 11 on to get from 18 to 29, you can then obviously just add the other semicircle on. And so 22 plus 7 is 29. So you can see how this 22 over 7 expression of pi, it very neatly fits in with the Lucas numbers. And this is how I'm going to show you. This is how the golden ratio, this is how the Fibonacci numbers particularly actually come into cosmology from the Pi-ness of Mercury. Now, I've just said Pi-ness, you can see what I mean. So the pi quality of Mercury. Now, I'll just recap. I'll remind you, this is what I showed in the previous session. Mercury is the red dot, Earth is the blue dot, and I've divided Mercury's orbit up into 22 steps, so I can count from a conjunction where they're both in a straight line with the sun in the middle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So there is the orbital period of Mercury. Now, if it goes another 7 steps, and bear in mind that's 22 and 7, 1, 2, 3, 4, 5, 6, 7, we get to the next conjunction. Now, if we keep on doing this and we go through this 22 plus 7, then we end up getting a 22 spoked wheel, you could say. And this is that 22 over 7 relationship that you find with Mercury. Now, I also mentioned how the sun's own cycle sort of works on the basis of 11 and 22 in the sense of 11 years and 22 years. So you could say that Mercury, as the first emanation out from the sun, in the sense of it being the first planet that's orbiting the sun, that sort of expresses the pi-ness that is there within the sun, and it shows itself in Mercury. But as I've mentioned, because you also have this possibility of Lucas numbers, then this is how we move from Mercury into the golden ratio of Venus. Now, as you can see, what you have in front of you is a star. It's an 11-pointed star. So 11 obviously relates to Pi-ness because of the 22-fold division of the circle. It's just giving 2 of those divisions for each one of these, just halving 22 down to 11. But 11 is also there in the Lucas numbers too. Right, now what we're looking at here is the orbital circles of Mercury and Venus. So Venus is the green one on the outside, Mercury is the red one in the middle. Now you see there's 2 circles I've marked around Mercury. Now they actually do relate very closely to the range within which Mercury goes around the sun, because Mercury has a very elliptical orbit. It's quite, it's known as its eccentricity. And the range within which it goes around the sun, in terms of it being out of kilter from an ideal circle, is within those 2 circles that I've marked there, one on either side of Mercury. Now, the distance of Mercury to Venus also relates to this star as well. So let's get moving. Now, what I'm going to do is allow Mercury to step in relation to the star. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 1 full orbit of Mercury. Now, if we carry on, having done 11, 1, 2, 3, 4, 5, 6, 7. Now they conjunct again after this relationship of 11 and 7. So there we have it again. We have this pi-ness that you get from 11 and 7, but we also have this potential for golden ratio because of the Lucas numbers, including 11 and 7. Now, having said all this, if I'm going to be completely honest, the really correct conjunction actually takes place slightly after that line, which is, the 7th point of the star. So what does this mean? Does this mean that I can't actually suggest what I'm suggesting and that I'm perhaps trying to fit it into place? Now, there's something very interesting that happens within this slight irregularity, which actually allows the Fibonacci numbers to come in. It's fascinating the way this happens. So we have Lucas, but with this movement from Mercury to Venus, Fibonacci numbers are going to become apparent through this irregularity. So let's just recap. I showed you how Mercury goes around 11 plus 7 times, whereas Venus has just moved 7 steps. Now, to get to this particular line in the star, to get there, it takes Mercury 144 days to get there. Now, with Venus, it takes Venus 143 days to get there. Now, it's really precise, really, really precise. It's 142.99 if you use the orbital period of Venus and work it all out with the mathematics. Now, the other interesting thing about this is that, obviously I'm talking about days. What is a day? It's the amount of time it takes for Earth to spin upon its axis. So this is where Earth Day becomes born. Very interestingly, this is where the Earth Day first shows itself in this relationship between Mercury and Venus. Right, I'm going to put these two sequences up. Here's the Lucas numbers and here's the Fibonacci numbers. Now, don't worry about reading them because I'm going to highlight these ones here. Now, as you can see, they're in the same position within the sequences in relation to one another. Now, what I'm going to do is color code them. So I'm going to color code the Mercury numbers, and you'll see why I'm saying Mercury numbers, with red. So 8 from the Fibonacci numbers and 18 from the Lucas. And then I'm going to do the other two numbers, 11 and 13. I'm going to color them green for Venus. Now, take a look at this. I just said about 144 being the Mercury number and 143 being the Venus number. Now, 8 times 18 is 144, whereas 11 times 13 is 143. Really beautiful concordance. So even though it's Lucas, if in the sense of it being 11 and 7 and 18, this is allowing the Fibonacci numbers to come in. And 8 and 13, they are essentially the numbers that are associated with what's known as the Venus pentagram. Now, I've got myself to my starting point with the Venus pentagram, but now this is where I'm going to stop the talk and draw a pentagram. I'll talk more about the Venus pentagram next week, but it's a fascinating sort of movement that happens from the Sun through Mercury and then onto Venus. Now, there's more to say about this next time, but for now, let's draw. Right, I'm going to stop sharing my screen and say hello. Oh, wrong camera. This is the one I want. Right, welcome everyone. I'm in a different venue this week. Now let me just spotlight myself for everyone. Okay. Thank you for turning up. It's late this evening, or at least for those of you who are in the same part of the world as me. So thanks for coming. Now we're going to draw a pentagram star, but we're also going to incorporate it into a decagon and also a pentagon. It'd be a pentagon, a pentagram star, and a decagon. So a decagon is a 10-sided polygon, the regular 10-sided polygon, because it has a very direct relationship with the pentagon and the pentagram star. So let's get drawing. I shall put my my camera on and the glasses go on. Now, as you can see, I'm actually just drawing on A4 this time. I've got this piece of A3 because it does actually affect the light of the camera, so it stops the camera becoming too bright, because the camera sort of calms itself down when it sees the large expanse of white paper. So I'm only going to be working within this A4 sheet of paper. Right, we'll divide a circle into 5 first. And in fact, this division of the circle, I'll talk about this next week because it has a really beautiful expression of the formula for the golden ratio in this particular division of the circle that we're going to do. Now, to begin, let's get 3 inches on the ruler. So a 3-inch radius, and that will fit on the page nicely. Now we're going to begin slightly off center in the page. And we also want to begin a certain number of inches up from the bottom. So I'm going to sort of hover my pencil around the middle of the page, and then I'm going to go 5 inches above the bottom of the page. So let me just lift that up so you can see it. So 5, put the pencil there, 5 inches from the bottom of the page. So 5 inches up from the bottom, and it needs to be sort of around the middle of the page. And we're not really concerned about going off, to be honest. But yeah, just to make it neat, have it around the middle, 5 inches up from the bottom. Right, so with your 3-inch radial measurement, draw a circle. Right, the next thing to do is to put in a horizontal line that goes through the center of the circle. And you could just go through the whole page. You might as well go through the whole page. Now, I should have said, actually, we are going to put pinprick holes through the paper and then draw on the other side. So you want to make sure that you have a piece of paper that's blank on both sides, and we'll draw the construction on here and the polygons on this side. Right, I'm going to place the point of the compasses in the eastern point of the circle, you could say, and make a mark up there and a mark down here. So marking here and here, just with that same radial measurement that you drew the circle with. And as you may expect, I'm going to do the equivalent thing on the opposite side as well. Right, I'm going to get the bisector. If you're used to geometry, you'll be well aware of what I'm doing. I'm going to put a cross above the circle like this by putting the point of the compasses there. Then the point of the compasses goes in here, and we get the other line. So we get this cross. Now this cross is essentially the middle path between these 2 points. I'm using the radial measurement of the circle. You can use any radial measurement, but obviously good to stay with what you've got. Now, having said that, when we put the equivalent cross down below, because of where we start on the page, you are going to need to reduce your radial measurement a bit to fit on the page. Feel free to do that. Now, once you've done that, we need to put in the bisector line. Now, having put in this line, I'm now also going to put in two more vertical lines. As you can see, those two marks that I made. Now, what these two lines should hopefully be giving us is the midpoint between center and circumference. So this one as well, midpoint between center and circumference. Now, technically, that should be the case. But if we haven't ended up drawing accurately, we'll become aware of that shortly, and we can just adapt our compasses. Because what we now need to do is to take this as a radial measurement. Now, I just went a bit quick there, so I shall give you a chance to catch up. Right, so as you can see, I'm taking this as my radial measurement. Now, I was just doing a bit of testing there, and I have actually put my point ever so slightly off my line here, where my line crosses the horizontal, because I want to be exactly at the midpoint between center and circumference. So through trial and error, because this line was obviously just a tiny bit off, because I want to have a circle which is going to very accurately go through the center and the circumference. Now I'm going to do the same thing on this side. Right, the next step is to put in a V shape. Now, as you can see, I'm going from the southern point of the circle and going all the way through that center of that circle there, all the way to the top, like so. Now, sometimes I refer to these as being the yin-yang circles, because this is how you draw the yin-yang pattern. So if we took, say, the lower semicircle there and the upper semicircle here, then we'd have that yin-yang pattern. Now, having put in this line here, I'm going to put the equivalent one in here. Now, we're only dividing into 5. If we were going to divide the circle up into 10, then we'd need to put in an equivalent upside down V as well. But this is all we need for 5. Now, what we have here actually expresses the formula for the golden ratio, but I won't go into that this week. I'll talk about that perhaps the next time or the time after. But it's this is my favorite division of the circle into 5 and 10, because it does just embody the formula. It's pure visual mathematics. Now, what we're going to do is take this radial measurement. So you're going to need to increase the radial measurement on your compasses just a little. Being a bit of a fusspot about my accuracy. So as you can see, point of the compass is there, and the pencil needs to be where the V is going through that circle, or that circle. Obviously, it should go through both points. Right, now I'm going to go up. It's quite a long stretch. Hope your compasses can do it. If not, then you'll have to go through this process when I put it online with a smaller measure. But I had quite a lot of spare on my compasses, so I'm assuming that it should be okay for you. Now you see how I'm just doing a small line from the top of the V and so here are my 5 points. Now, be really careful. Make sure that you get the correct point here, because these 2 points, being as they're so close together, can sometimes get a bit mixed up. So make sure it's the point coming from the curve that you've drawn, not the point coming from the straight line. Very common mistake, which us teachers sometimes make too. Now this is the 5-fold division of the circle, but having drawn this on this side, I'm going to put pinprick holes through, and then we'll turn the paper over and work on the other side. So I'll give you a minute or two to reach that point. Right, so having marked these 5 points, I'm going to turn over and see my pinprick holes here. I'll make these 5 points clear by drawing a pentagon, and then we can sort of see what we're working with. So the pentagon, the regular 5-fold polygon, that is what I'm going to put in first. Now, the next thing I'm going to do is put in the pentagram star. So as you can see, if you've got 5 points, you can either just go to the next door point, or you can skip 1 point and go to the next point. Now, if I were to do that going in this direction, I'd skip that point and go to there. So it'd be like an equivalent line to this. And as you'll see it, this is, I mean, this is actually the first division of the circle where you can draw a polygon star. And you just get one. So you get the polygon and the polygon star. So I'm going to do this. And as we'll see next week, this is actually the geometry plotted out by the planet Venus in its relationship with planet Earth. having put in this pentagram star, there's now an immense number of golden relationships. So in the sense of the relationship of a greater to a lesser part that is in the golden ratio. Now, for instance, if this pentagon has an edge of 1, then the line of the pentagram would be 1.618. Now, if this small pentagon here, if that has an edge of 1, then that is 1.618. And in fact, this is a very significant triangle, partly because this angle is exactly half the size of these two angles. That's 36 degrees, that's 72 degrees, so those two there. I talk about this triangle and various other golden ratio isosceles triangles in my book, in fact. Now, if we look upon this line here, well, actually, let's go with this line here. This line here is cut at the golden section here, so you've got lesser to greater, but it's also obviously cut at the golden section here if we just flip it around, so lesser to greater. Now, the last thing we're going to do is place a point of the compasses into the top, like so, and then reduce our radius so that we have this measurement on the compasses. So as you can see, it's the edge of one of these isosceles triangles. So the point of the pentagram star. Now, the reason why I'm focusing on this triangle here is that this is actually one sector, or one cake slice, you could say, of a decagon. So we can actually bring the decagon into this diagram, and this is going to be the center of it, where we have the point of the compasses. So we're going to draw a circle, like so. Now I'm going to do this circle a little bit lighter, but then do the decagon inside it in darker line. Now here we already have 3 edges of the decagon. If I do this, and if I do this. So this is another pentagram point, as is this, or 3 sectors, 3 cake slices of a decagon. Now, the other thing is that this line, where it reaches this line here, it cuts it at the golden section. So again, we have lesser, greater. Now I'm going to extend lines to finish this off. So as you can see, I'm going very carefully along this line here. So be careful to get it accurate. And I'm going to extend up like that, and then do the equivalent thing here as well. Now we can do similar thing with the edge of the pentagon as well. Those of you who've drawn 5-fold patterns before will be very familiar with what I'm doing here and how it does have this capacity to bring itself to completion, often just through extending lines in the way that I'm doing. Now let's put those edges in too. Now, as you can probably see, we just need to have a horizontal line going through here. Now, there's various different ways that we can go about that. I'm going to just use the simple bisector. And let's see, well, compasses. Yeah, you can even just use the same measurement that you already have on the compasses from drawing this circle. So you see how I'm using that corner of that one there and an equivalent one here, and make sure it's the equivalent, because you can see these are equivalent points. So again, I'm just finding the middle way between them, and I'm going to do the equivalent thing here as well. Now there's always various different ways of finding these relationships, so this is just one. Now, I'm not going to put the whole of this line in. I'm just going to put in where it goes through the circle, like so. And so now I can obviously finish off my decagon. Now, the decagon also shows itself in the orbital relationship between Earth and Venus. So that's another thing I'll point out at one of the upcoming sessions. Okay, everyone, I'm going to come back to finish off the session. Now, I am going to show just one thing. I'm going to show a flyer for a course that I've just set up. It's going to happen in the city of Wales between Palm Sunday and Easter Sunday. It's actually going to be an 8-day course. We won't be sort of working for the whole of the 8 days. There'll be various other things going on as well, such as walks in the local area. But let me just get my slides back on again. I'll share my screen. Right, so here's the flyer. Now I'm going to attach this flyer to an email. Oh, I'm going to attach this flyer to an email soon as well. So if you're on my mailing list, you'll be able to get this. If you're not on my mailing list, then feel free to contact me. In fact, the email address on this flyer, you'd be able to get onto my mailing list through that. That's really specifically the email address for the courses that I run in Wales as part of the Wales Institute for Sophia in Education. So hence wise in Wales at gmail.com. Now, there'll be about 6 days worth of study, and there'll also be walks. So we're going to do a full moon walk. The full moon during Holy Week is actually on the Annunciation this year. So that's quite a nice symbolism for that. Easter's very early this year. It's Easter is the first Sunday after the first full moon, after the spring equinox. So it happens very early this year, according to that calculation. Now, I will also do an Easter morning walk, and it's a lovely walk close to Wells, which involves quite a steep ascent through a gorge to a beautiful viewing point. And of course, because it's Palm Sunday to Easter Sunday, there'll be all of the Easter choral music and liturgy as well, which you can go to, or if you don't want to go to that, you can go for a walk or have some silent meditation or whatever. So I'll attach this flyer to an email too, but do come along to Wales if you fancy it. And it's going to be a real in-depth study of my book. So it'll be a good 6 days worth of going into certain parts of the book, and we can obviously have lots of conversations about it as well. So if you've been reading my book and you have any questions, then it's an ideal opportunity to ask them and for us to talk about stuff to make things more clear. Now, as for the next session, we'll go back. So the next session is actually going to be, well, at the very end of what we call Boxing Day in the UK, or the Feast of Stephen, 26th of December. So it's going to be literally at midnight as we go into the 27th, which is the Feast of John the Evangelist. That's one of the two sort of main days in Freemasonry. They have St. John in midsummer and St. John in midwinter. So it'll be at midnight. So do please join me if you can. It's obviously a time when you're quite possibly going to be with people, but if you can't join me, it'll go online anyway. So, but yeah, do come and join me. It's quite nice doing geometry at night, actually. It's quite a different feeling to when we did it in the morning on the past 2 sessions. So thank you for coming to this session, and do keep coming. I'm really enjoying doing them, actually, because obviously I don't need to care about the time. I don't have to fit into any sort of time limit. I've gone on for an hour this time, and they're supposed to be half an hour, but you know what I'm like. I just once I get talking, I can't really stop. So the next one on midnight at the very beginning of the 27th of December, and that will, again, we'll go more into the golden ratio and how it shows itself in Venus cosmology and so on, and also in the design of Wells Cathedral, because that's really what I'm trying to do with these classes, to sort of broaden out a bit on the subject matter in the book and show the cosmological underpinnings of it all. So I shall see you in 2 weeks' time if you're free to come, and I hope you have a good sleep for those of you who are in a similar part of the world to me, or a good day if you're somewhere else. So come again. See you next time. Bye.
Thanks, Tom. Bye-bye. Thank you.
Thank you. Thank you.
Thank you, Tom. Thank you. Bless you.
Bye.
Thank you, Tom. Bye-bye.